Internal energy is the total energy contained within a thermodynamic system. This energy includes the kinetic energy of the molecules. Internal energy also includes the potential energy associated with intermolecular forces. Temperature is a measure of the average kinetic energy of the molecules within a substance. Kinetic energy refers to the energy an object possesses due to its motion. Temperature is related to the average speed at which molecules are moving. Molecules are in constant, random motion. The speed of molecular motion corresponds to the temperature of the substance. Faster molecular motion indicates a higher temperature. The kinetic theory of temperature posits that temperature is directly proportional to the average kinetic energy of a substance's particles. Increased temperature corresponds to an increase in the average kinetic energy of the particles. The kinetic energy of particles is the primary factor determining a substance's temperature. Internal energy represents the total energy contained within a system. Temperature is a measure of the average kinetic energy of the particles within a system. Internal energy includes all forms of energy, while temperature specifically reflects the average kinetic energy. Adding heat to a metal block increases its internal energy. Increased molecular vibration corresponds to a rise in temperature. Heat addition causes molecules to vibrate more vigorously. Cooling a gas reduces the kinetic energy of its molecules. As the gas cools, the molecule's velocity decreases, lowering the internal energy. The reduction in molecular kinetic energy directly results in a lower temperature of the gas. Energy transfer occurs through three primary mechanisms: conduction, convection, and radiation. Conduction involves heat transfer through direct contact, where energy moves from hotter to colder regions. Convection involves heat transfer through the movement of fluids, liquids, or gases. Conduction is demonstrated by heating one end of a metal rod. Heat transfers through the rod as molecules vibrate and collide. Molecular collisions facilitate the transfer of thermal energy along the metal rod. Convection is demonstrated by heating water in a beaker. Warmer water rises due to its lower density. Cooler water sinks, creating convection currents within the beaker. Radiation is the process by which energy travels through space from the sun to the earth. This energy transfer occurs without the need for a medium, unlike conduction or convection. The sun's energy warms the earth through electromagnetic waves, a form of radiation. The experiment involves measuring the temperature change of water as it is heated. Temperature change is recorded at regular intervals to track the heating process. The rate of temperature increase can be analyzed to understand heat transfer. Ice melting experiments demonstrate energy transfer by observing changes under different conditions. Variables such as ambient temperature, insulation, and airflow affect the rate at which ice melts. The experiment illustrates how energy is absorbed by the ice, leading to a phase change from solid to liquid. Thermal conductivity measures a material's ability to conduct heat. In this experiment, students compare the rate of heat transfer through various materials. Materials with higher thermal conductivity transfer heat more rapidly. Internal energy is directly proportional to the mass of a substance. A larger mass contains greater internal energy at the same temperature. Different substances possess varying internal energies even with identical masses and temperatures due to their unique molecular structures. The type of substance affects internal energy because different materials have different specific heat capacities. Heat input directly influences temperature change. Increased heat input generally leads to a higher temperature. Specific heat capacity is the amount of heat required to raise the temperature of 1 unit mass of a substance by 1 degree Celsius. Substances with higher specific heat capacities resist temperature changes more effectively than those with lower specific heat capacities. Specific heat capacity is defined as the amount of heat needed to raise the temperature of 1 kg of a substance by 1 degree Celsius. This property quantifies how much energy a substance can store for a given temperature increase. Specific heat capacity is measured in joules per kilogram per degree Celsius, J, kg, du4, C. Water's high specific heat capacity means it requires a significant amount of energy to change its temperature. This property makes water an effective coolant, absorbing heat without drastic temperature fluctuations. The stability of water temperature is crucial in many applications, from industrial cooling to climate regulation. Metals exhibit low specific heat capacity, meaning they require less energy to change temperature. Due to their low specific heat capacity, metals heat up and cool down rapidly. The rapid temperature change in metals is due to their efficient energy transfer at the atomic level. Engines convert internal energy into mechanical work, powering vehicles and machinery. Refrigerators utilize energy transfer to cool food, maintaining lower temperatures inside. These applications demonstrate the practical use of internal energy and temperature control in everyday technology. An internal combustion engine converts the chemical energy of fuel into mechanical energy. The combustion process inside the cylinder drives the piston, which in turn rotates the crankshaft. The rotating crankshaft provides the mechanical power to propel the vehicle. Refrigerators utilize energy transfer to remove heat from their interior, maintaining a cold environment. The refrigeration cycle involves the circulation of a refrigerant that absorbs heat inside the refrigerator and releases it outside. Key components, such as the compressor and condenser, facilitate the heat transfer process, ensuring efficient cooling. Insulation materials reduce energy transfer between a building's interior and exterior. Effective insulation helps maintain a consistent indoor temperature, keeping buildings warm in winter. Insulation also keeps buildings cool in summer by preventing external heat from entering. A thermos flask minimizes heat transfer through conduction, convection, and radiation. The vacuum between the double walls significantly reduces heat transfer by conduction and convection. Silvered or mirrored surfaces on the glass walls minimize heat transfer by radiation. Internal energy represents the total energy contained within a thermodynamic system. Temperature is a measure of the average kinetic energy of the particles in a system. Energy can be transferred through conduction, convection, and radiation.